Hello, this is Xiaowei from the Graph Systems Lab of Ant Group. Today, I will give a short talk about our experience of adapting an academic prototype graph processing system to industrial application. Before introducing our story, let me first give some brief background information regarding graph processing. Graph structured datasets model real-world entities with vertices and their relationships with edges. For example, in the Alipay ecosystem, we can model user accounts and their associated items such as used mobile phones and bank cards as vertices, and connect them through various types of relationships such as payments, transfers, friendships, and so on. So, how can graph processing help the business? Here, I list a few representatives. Reachability analytics such as Fortis path computation can help us identify potentially suspicious users from known frauds. Importance analytics can rank vertices by some inherent topologic properties. Community analytics can detect various types of communities and is useful in many scenarios. Well, how can we process graphs efficiently, especially those of internet scales? A first thought is to use existing big data systems such as Hadoop MapReduce and Spark. The process mainly consists of iterative drawings and group-by aggregations. However, due to several unique challenges of graph processing, this is usually quite inefficient, and processing a small graph may already consume a lot of resource. To this end, a lot of systems designed specifically for graph processing have been proposed. Here, I only list probably two of the most well-known systems. The first is Prego, which describes the think-like-a-vertex programming paradigm. Computations are performed surrounding vertices, with messages propagate between vertices for information exchange. The second is PowerGraph, which presents an elegant solution to skewed degree distributions commonly seen in natural graphs. The central methodology here is to split a vertex into multiple replicas, and thus distributed computations onto multiple partitions. Now comes the main character of today's talk. We developed a research prototype system called Gemini, which forms the foundation of G-Compute now at Ant Group, used for offline graph processing. The goal of Gemini is to bridge the performance gap between shared memory graph processing systems and distributed alternatives at that time. The main proposed message in the paper is that we should build scalability on top of efficiency by avoiding unnecessary distributed overheads and optimizing local computations on partition subgraphs. Well, the focus of today's talk is not about the technical contributions, but the following. As with existing work, we made some implicit assumptions. Actually, the latest graph processing papers to date still implicitly have those assumptions. While they all look reasonable from the academic view, are these assumptions really valid, especially under industrial settings? Let's review them one by one. The first assumption is about the existence of supervertices due to the power law phenomenon in real-world graphs. Apparently, the existence of such vertices is harmful to load balance. Hence, splitting the computation of each vertex to multiple workers always looks like a good idea. So even though Gemini adopts edge cut rather than vertex cut partitioning, we managed to split the computation with co-designed data organization and processing model. Okay, so how about the fact? Well, we find that degrees are indeed scaled, but in many cases, those vertices with extremely high degrees can be pruned, harmlessly without affecting the algorithmic effects. Another related and probably more important fact is that some applications prefer centralized processing, for example, community detection algorithms like LPA. However, many distributed forms of graph processing models, such as Power Graph's getter applies getter and Gemini's signal and slot, would suffer from expensive communication costs in these cases. The next assumption is that preprocessing is expensive compared to actual processing, but can be amortized across multiple jobs, so it is only a one-time cost. While the previous assumption is partly true, this assumption is unfortunately almost completely invalid. In our production environment, nearly each job uses a new graph as input, so there exist very few opportunities for sharing preprocessed results. This is due to the fact that each job applies different filters and projections to extract the input graph from upstream data sources, and only when multiple algorithms can share a common graph as input can such sharings happen, which usually occurs only in development stages. The third assumption is that graph processing systems run on powerful clusters. Each node is given sufficient memory and can communicate efficiently with each other. Actually, many research papers argue that a single node equipped with terabytes of memory can handle most large-scale graphs and thus focus on improving the single-node shared memory graph processing system. Even when a single node's memory capacity is not enough, we can add more machines and rely on fast networks. Unfortunately, the fact is that for a shared cluster in production environments, we can only utilize virtualized small containers with limited memory, and that network is not fast enough to make techniques like memory disaggregation practically useful. Well, it seems that these assumptions all deviate from reality to some extent. So how can we address these unexpected but essential needs? Our lessons can be summarized as two messages. First, space or memory cost is probably more important than other factors, since suboptimal memory usage could make a job fail with given limited resource. Second, preprocessing deserves more attention as they are not just one-time overheads, but rather an essential part of the whole processing pipeline. Well, personally, I would suggest that all graph processing papers in the future to also study and analyze the preprocessing performance in terms of both time and space. To cope with these issues, we applied quite a few important optimizations on top of the core Gemini engine, and most of them are space-oriented. We first focus on improving the efficiency as well as space usage of preprocessing phases. For edge sorting, we switch from the original counting sort that includes multiple passes of input data transfers from the data source to quick sort that requires only one pass, and finally choose an in-place radical sort that is both time and space efficient. Another interesting choice is the implementation of 40-bit integers for vertex identifiers, and this allows larger capacity than 32-bit integers, but is enough to hold a trillion vertices and a lot more space efficient than 64-bit alternatives. As for the processing engine, we also incorporate a set of important optimizations. The largest change is that we decouple the computation and communication engines to enable more flexible push and pull choices. Importantly, dual mode is now optional so as to trade some efficiency losses for space savings as well as reduced preprocessing costs when necessary. Centralized push and pull style processing are also enabled. The last important space-oriented decision change is regarding message processing, which shifts from bulk processing to a streaming fashion. Well, is that all? Some of you might feel a bit depressed because I only mentioned the shortages of our research prototypes till now, and it seems that academic systems would expose quite some weakness in industrial scenarios. So in the final part of this talk, I will show you some positive aspects. Actually, Gemini-based G-compute is nearly an order of magnitude faster than previous approaches, and also consumes significantly less memory, even before our modifications. This opens up some new options to be explored. For instance, we are now encouraging our users to keep more vertices and edges for analytics whenever the resource quota allows. While pruning super vertices is harmless, keeping them is harmless as well, and may reduce many data cleaning efforts. Next, how about using large containers, or even bare metal instances for graph processing? Actually, allocating only small containers has some historical reasons, as previous generations of graph processing solutions cannot benefit much from powerful, larger containers. But for a high-performance graph engine like Gemini, the cost efficiency may be higher when each worker can use more compute and memory resources, since the number of partitions may decrease, which usually leads to reduction in overall communication volume that may become bottlenecks. And thirdly, though I said previously that preprocessing costs can hardly be amortized across multiple jobs in G-compute's current form, such kinds of overheads may be largely reduced or even eliminated in cases if we can perform graph processing in an H-type system. Actually, the analytical latency and result freshness may also be improved. This is one important direction we are exploring right now. Before concluding this talk, please allow me to post a short advertisement. We are looking for researchers who are interested in building all kinds of cutting-edge graph processing systems. Collaborations are also welcome. And that's all for my talk today. Thanks for listening.